Welcome to the finance section. Before covering this topic, you should have already covered logarithms and the sequences and series sections. As the very first part of the topic uses logarithms, and the leftover parts use formulas related to sequences and series. So you'll be pretty lost if you haven't studied them already. That being said, here's the topics to be covered. First, we'll focus on questions where you need to determine the period of investment. Then we'll cover annuities, which is made up of subsections, present value annuities and future value annuities. And lastly, we'll use the methods learned from the previous sections to analyze different loan and investment options. Let's begin. Before covering the new material, let's just brush through what you should be familiar with from before. First, there's different types of interest, these being simple and compound interest, whose terms are as described in this image, where P means the principal or original amount invested, A means the total amount of money accumulated after the investment earns an interest at a rate I over a period of time N, represented in years. Something very important to note is that this interest rate will usually be stated as a percentage, and I represents the interest rate as a decimal, so you have to divide the percentage by 100 before substituting it into the equation, otherwise you'll just get some crazy numbers. Then there's the formulas for depreciation, which are very similar to the formulas for interest, but they have minus signs in the middle instead of plus signs, since depreciation represents a drop in value with time. This time, I would represent the depreciation rate and not the interest rate. And lastly, there's the formula for effective and nominal interest rates, which is related to interest rates that are compounded more than once a year and whose interest rate is usually stated as some percentage per annum, this being the nominal rate. But if you were to actually calculate the total amount of interest that compounds over the year, it would be slightly different. This formula allows you to convert between the nominal rate and the effective rate based on how much interest is actually earned over the year. M represents frequency per annum, meaning the number of times the interest compounds in a year. If it compounds quarterly, M would be 4. If it compounds biannually, so twice a year, M would be 2. And if it compounds monthly, M would be 12. Now moving on to new material, first we have period of investment. Period of investment isn't anything so new. It just means using the same formula, which you know from before, but solving for N this time. For the two simple equations, it's pretty easy to just rearrange and make N the subject. But for the compound formulas, since N is an exponent in this case, it's a little bit trickier to make it subject, which is where logarithms come into the picture. Let's look at an example. You plan to invest 100,000 Rand with the aim of growing it to 150,000 Rand. You look at the options available at two different banks. Bank X pays simple interest at a rate of 8% per annum, and Bank Y pays 6% per annum compounded yearly. Which bank will meet your goal the quickest? You want to invest 100,000, so your principal amount P is 100,000, and you want it to grow to 150,000, so accumulated amount A is 150,000. Since they asked which bank will meet the goal the quickest, you want to find out the period of investment for both cases, so the value of N. We'll look at each bank separately, starting with Bank X. It pays simple interest at 8% per annum, which is 8 over 100, which is 0.08 as a decimal. Here's the formula for simple interest. Then just simply rearrange to make N the subject, finally giving you N equals to 1 over I times brackets open A over P minus 1 brackets closed. And we have all these values which we need to sub in, and when you sub these in, you finally get the answer as 6.25 years. Then let's look at Bank Y. The question said its interest rate is 6% compounded yearly, so its I value is 6 over 100, or 0.06. And here's the formula for compound interest. Then rearrange to make N the subject, and this is where you would normally get stuck. But since we're familiar with logarithms, and we know how to use logarithms to make n the subject, if you convert this to a logarithm form, you would get n equals to log a over p base 1 plus I. And if you have a calculator which can solve logarithms in this form, we can just sub in the values directly and get the final answer. But if your calculator can't solve it in this form, you can solve it by converting it using the first log manipulation rule, which was log a base b is equal to log a over log b. So applying this gives n as being equal to log a over p over log 1 plus I. Then you can just sub the values and solve, which finally gives n for bank Y as 6,96 years. The different period of investment we got for the banks were 6,25 years for bank X and 6,96 years for bank Y. Therefore, bank X would meet your goal the quickest. Here's another example. Jill plans to invest at a rate of 15% compounded biannually. How long would it take for her investment to double? This example has two new things. The first is it involves an interest that compounds more than once a year, and also it doesn't include any actual amounts of money. It just vaguely asks how long would it take for her investment to double. Another way of saying this is how long would it take for the principal, meaning original amount, to double, meaning the time required for accumulated amount to equal double the principal amount. Put simply, this means time required for A to equal 2p. The interest is at a rate of 15%, so 0.15 in decimals, and it compounds biannually, so twice a year, meaning the frequency per annum, or m value, is equal to 2. This is the usual compound interest formula. But when the interest compounds more than once a year, it's slightly different. This time it also includes m, so the I value is divided by m, meaning represents the interest rate per period, and the exponent is n, meaning number of years, times m, which is frequency per year. Therefore it represents number of periods in total. It's very, very important that the time units for I should be the same as the time units for the time period n, or the exponent rather. So if the interest compounds twice a year, the time period of which interest compounds is half a year. So divide I, which represents interest per year, by 2, so it represents interest per half year. Then the exponent should be number of half years over which interest is accumulated. So you multiply number of years by number of half years per year, so a frequency of 2. Anyway, we'll see that just now. Firstly, you want to make n the subject of this formula. So you'd first take p that side and divide a by p. And since we established that a equals 2p, a over p would just be 2. Then you convert to log form and apply the same manipulation rule, giving you m times n equals to log 2 over log 1 plus I over m. Then you can finally make n the subject by taking m to the other side, finally giving you n equals to 1 over m times brackets open log 2 over log 1 plus I over m, close brackets. Then you can just sub in the values, finally giving you n as 4,79 years. So it would take 4,79 years for Jill's investment to double. Then, for the final example under period of investment, Jacob buys a new car for 245,000 Rand, and it depreciates at 16% per annum on a reducing balance basis. After how many years will the vehicle be worth less than 105,000? Notice that this question now talks about depreciation, meaning you won't only be asked questions related to interest and period of investment, you can also be asked related to period of depreciation, but it's pretty much the exact same process. You just use the equation for compound depreciation instead of the equation for compound interest. In this example, the principal amount is 245,000 and the accumulated amount is 105,000 since the car value reduces with time. Then they said that it depreciates at 16% per annum on a reducing balance basis. Reducing balance just means compound depreciation. And make sure you're familiar with this terminology and remember what it means, because you could just use the term randomly in a test or exam, so you should definitely know what it means. So it depreciates at 16% per annum, which is 0.16. The equation for compound depreciation is accumulated amount equals to principal amount times 1 minus I to the power of n. Then just rearrange like before to make n the subject, and you can just sub in the values now, giving you n as 4.86 years. Therefore, the vehicle will be worth less than 105,000 Rand after 4.86, or approximately 5 years. Moving on to the next section, annuities. Annuities are a series of payments of a certain fixed amount of money at regular intervals for a certain period of time. Examples of this include paying back a loan or making regular deposits to a savings account. Annuities are subject to a rate of interest. There's two types of annuities we'll cover. First of these is future value annuities. In future value annuities, payments are made at regular intervals, each of which earns interest. And the whole point is to accumulate a certain amount of money for a certain point in the future, such as for a retirement fund. Here's an example. Joy deposits 1,000 Rand into a savings account at the end of each of the following 4 years. If the money earns interest at a rate of 6% compounded yearly, what would his saving be after 4 years? I'm using this example to demonstrate how the equation for future value annuities is derived. You don't need to know how to do this proof, but I strongly suggest you put some time into following and making sense of it, as it will give you an intuitive understanding of where the equation comes from. Moving on, first piece of advice I'll give you for when you see these types of questions is draw a timeline. This will give you a much better idea of what's happening with all the money. The timeline for this question would look something like the following. We have the points in time written at the top, and the money being added or removed at that point in time at the bottom. So here at the top, you could have just written these as 0, 1, 2, 3, and 4. I just personally prefer this notation with the T, but it's entirely your choice. It just needs to make sense. So T0 means right now, and since it says he deposits 1,000 Rand, you put 1,000 at the bottom. Then it says he deposits 1,000 Rand at the end of each of the following years. So T1 means after 1 year, T2 after 2 years, and so on. His deposits finally end after 4 years at T4. So how do we determine how much is in the account at the end of the 4 years? Previously, you looked at cases where a single deposit is made now, and then you just need to determine how much interest it gains over a certain amount of time. But what's tricky about this situation is now you have multiple deposits at different points in time, and each is in the bank for a different amount of time, so each earns a different amount of interest. So how do you determine the total that all of these add up to? It's quite simple. You would just do the usual calculation using the compound interest formula, but separately for all the different payments. Then you just add up all the different results to get your total. So each deposit is 1,000 Rand, so each deposit initially has a value of 1,000, so P is 1,000. Then they said that it gains 6% interest per annum, compounded yearly, so I is 0.06. Now remember, we are going to do the calculation for deposits made at different points in time, meaning they sit in the account for different time periods, so the value of n will vary. What range of n values would there be for this case? Let's look at the timeline again. The largest value of n would be for the very first deposit, since it would earn interest for the greatest amount of time, this being 4 years. So the highest value of n is 4. Then the second deposit would sit in the account for 3 years, meaning an n value of 3. And the third deposit would have an n value of 2, and n keeps reducing till you reach the final payment made at the end of the 4th year, which would have an n value of 0, as it was just deposited at that point. Therefore, the range of n values would be from 0 to 4. Now we just need to do this compound interest calculation for all n values in the range. Let's start with the very first deposit when n equals to 4. If you sub in the values, you get 1000 times 1,06 to the power 4. Then you just repeat this calculation for all other n values and get the following: 1000 times 1,06 cubed for n equals to 3, 1000 times 1,06 squared for n equals to 2, 1000 times 1,06 for n equals to 1, and 1000 times 1,06 to the power 0 for n equals to 0. So I've left them all in this bracket form and didn't calculate the actual values so I can show you something. Now you have all the accumulated amounts at the end of the 4 years for all the deposits. So to get the total, you just need to add these together, which looks like. Then if we arrange them from smallest to biggest, this first term would just be 1000, since 1,06 to the power of 0 is just 1. The second term would be 1000 times 1,06, and the rest of the terms would remain exactly the same. Notice something. The first term is 1000, and the second term is just the first term times 1,06, and the third term is just the second term times 1,06, and this is the same for the fourth and fifth term. You've previously seen this sort of thing before, and that's under the sequences and series section. All of these terms would represent the terms of a geometric sequence, and since you're adding all of them up together, this would represent a geometric series. As a reminder, here's the nth term formula of a geometric sequence, where a means the first term, which would be 1000 in this case, and a constant ratio r of 1,06. And n represents the number of terms, which would be 1, 2, 3, 4, 5. 5 in this case. So to find the sum, we can just use the equation for geometric series and sub in the values, which gives the total saving as 5,637 Rand and 9 cents. So that example showed that we can calculate the total saving for a bunch of deposits quite quickly by representing them as a geometric series. Therefore, we can derive a general formula to determine the sum of a number of regular deposits n of an amount x, each subject to an interest rate I at the end of a certain amount of time, so a future value. So the equation we used before for a geometric series works better for cases where constant ratio r is less than 1. But for cases where r is more than 1, a different form of the same equation works slightly better. And you can get this form by just multiplying this equation by 1, meaning it's the same equation. But you write 1 as -1 over -1, which allows you to swap around these terms and get, which works better for cases where r is more than 1, which applies to our current case. So the regular amount you deposit, which I defined as x, is what you deposit the first time as well. So the first term a can be replaced with x. Now remember above, we had determined the constant ratio in the example as 1,06, which is the same as 1 plus the interest rate I. So r can be replaced with 1 plus I. And the sum Sn is the future value f. Subbing these all into this equation gives, therefore, the final equation to calculate the future value of a bunch of regular payments would be this equation, where f represents future value of the payments, x is the regular payment amount, I is the interest rate, and n is the number of payments. We can now just apply this nice equation to the same example instead of doing all those long calculations. The regular deposits were 1000 Rand, so x equals to 1000. The interest rate was 6%, so 0,06. The values of n, which represented time period in the compound interest formula, was 0 to 4. But for this equation, n is a little different, and n instead represents the number of payments, which was actually 5. So for this new equation, n equals to 5. Then you just sub them into the equation and finally get the answer as 5,637 Rand and 9 cents, which is exactly the same as the answer we got before. Therefore, we know the derived formula works. Let's look at another example. Nell decides to start saving some money for the future. At the end of each month, she deposits 850 Rand into an account in Bank Z, which earns 8.4% interest per annum compounded monthly. First question is, how much money has she saved after 25 years? First thing to notice is that this example is different in that this time the payments are on a monthly basis, whereas for the previous one they were made on a yearly basis. Also, in previous example it was just 5 deposits made over the course of 4 years, so it was simple to draw the timeline. But this time the deposits are made every month, and that too for 25 years, so it wouldn't really be feasible to draw the entire timeline, but we can still sketch a basic version. So you have the first few like normal, then you have many others in between, and eventually end up at the final deposit at the end of the 25 years. One very important thing to notice is that this time an initial deposit wasn't made, so the value at T0 would just be 0. Therefore, since a deposit is made at the end of each month after, the total number of deposits would be 12 deposits a year times 25 years, which is 300. So number of terms n for the future value equation would be 300. So whenever there's an initial deposit, like in the previous example, you'd calculate number of deposits by multiplying deposits per year by number of years, then adding 1 to it. That's why in the previous example, the value of n, which we substituted into the future value equation, ended up being 5 because you had the 4 deposits at the end of each year plus the initial deposit as well. But in this example, there's no initial deposit, so n is just 12 times 25. But if there actually was an initial deposit, you would add 1 to this and n would be 301. So keep this in mind because most students mess up these annuity calculations in exams because of messing up with the interpretation of the value of n. Anyway, moving on, they told us the interest rate is 8.4% per annum compounded monthly. So you divide the rate by 12 since you need to find the interest rate per month since you're making monthly deposits. This comes back to what I stated earlier, that the interest rate and the n value should have the same time units. And when you do the calculation for the interest rate, you get the value as 0.007. Lastly, the monthly deposit is 850 Rand, so x equals to 850. Then you can just sub these into the future value equation, which finally gives the total future saving as 862,949 Rand and 77 cents. Then the second question was, how much interest did she earn over 25 years? So the final account balance, meaning the future value f, is equal to the sum of all the 850 Rand deposits made in the 25 years plus all the interest earned on these payments. Then just rearrange to make the interest the subject. We already have the final account balance, which we just calculated in part 1. And to get the total deposited, we just multiply the number of deposits by the amount of each deposit, which gives the value as 255,000 Rand. You just sub these all in and get the total interest as 607,949 and 77 cents. One last important thing to keep in mind before I move on to present value annuities is that since you're dealing with many different big numbers, and since you need to write down the results of these different calculations, you usually round them off before writing them. You would then be tempted to do later calculations using these rounded off values. Absolutely avoid doing this. Using rounded off values will lead to your final answers being off by a small amount, for which you'll be marked wrong in the exam. You should rather save the different values you get as variables on your calculator, then use those saved variables in any later calculations, so you don't lose any accuracy in your final answer. To put it simply, don't use rounded off values in calculations. Always use exact values. Moving on to present value annuities.